Hello everyone, this is Siddhartha Pramanik, a research scholar from the Department of Mathematics, IIT Kharagpur. So this is the live session for week 3. So I will be solving some problems related to the content of week 3 and which does not coincide with the assignment of week 3. So meanwhile, if you have any doubt in the content of week 3, you can ask here by unmuting yourself or by putting in the chat box. Uh, so I will start solving some problems. So I will write down the problems first and try to explain them. Then I will ask you if you have any guesses for the answers or any solutions. And then I will give you the complete solution. So I hope that is fine for you. Okay, so first let me write down the keywords for the week 3. So the problems will be based on those things only. So in week 3, we have saw what do we mean by group isomorphisms. And after that, we have saw about a special kind of subgroup, namely normal subgroups. And then we have saw about the cosets. And finally, we have saw the celebrated theorem, which is Lagrange's theorem. So this fourth topic is the keywords for this week 3. So let me start by giving some problems on group isomorphisms. So first I will list down some properties of group isomorphisms which will help you to decide two groups are isomorphic or not in the problems of this season and also for the assignments. So let me write down the properties. So properties of group isomorphisms. So recall that a group isomorphism is a bijective function uh, which is also a group homomorphism. So let phi from G to G prime be a group isomorphism then the following properties hold. So first one is, since phi is bijective, phi inverse is also bijective. So the inverse function from G prime to G, it is also a group homomorphism. In fact, it's a group isomorphism. Okay. So next one is uh, the group G is abelian if and only if the group G prime is abelian. Third one is G is cyclic if and only if G prime is cyclic. Okay. And next one is if H is a subgroup of G, then that will imply the image of H, which is phi of H, it is also a subgroup of G prime. Fifth one is, so if we take a subgroup in G prime, then the inverse image of that will be a subgroup. So if H prime is a subgroup of G prime, then phi inverse H prime is a subgroup of G. And sixth one is, we all know about the subgroup known as center of a group. So if we take the image of the center of G, it is exactly same as center of the group G prime. And finally, the seventh one is, uh, if you take an element A in G, then order of the element A is same as order of the image of this element. Okay, so let me read out the properties again. So given is phi from G to G prime a group isomorphism, then we have these following properties. First one is inverse function from G prime to G is also a group isomorphism. Second one is G is abelian if and only if G prime is abelian. Third one is G is cyclic if and only if G prime is cyclic. Fourth one is if you take a subgroup in G, its image is also a subgroup in G prime. Similarly, if you take a subgroup here in G prime, its inverse image is a subgroup of G, which is the fifth one. Sixth one is saying image of the center of G is same as center of G prime. And last one is in G, if you have an element A, then order of A is same as order of the image of A. So I will not prove all these properties uh, because these properties are very easy to prove. So I will prove very few of these. Okay, so let me prove only sixth one and seventh one. So you can try other properties by to prove on your own, and if you are not able to do, you can come back in next season, and I will try to clear your doubt. So let's prove the sixth one. So we need to prove image of center of G is same as center of G prime. So basically you need to prove these two sets are same. Same means they are equal. So the standard trick is we need to prove the both side inclusions. First one is this side and second one is this side. So let y belongs to phi of zg. So we need to prove y belongs to z of g prime, right? For one side inclusion. So this implies y equals to phi of x for some x belongs to z of g. This is by definition. So we need to prove y belongs to center of zg prime. So that means y commutes with every element of g prime. So if y prime belongs to g prime, then there exists an element, let's say x prime in g, such that phi of x prime is equals to y prime. This is because phi is bijective, right? So phi is surjective also. Now uh, x prime x is same as x prime, right? Since x belongs to z of g. So you apply the map in both sides. So phi of x prime x is same as phi of x prime. Now phi is also a group homomorphism, right? So phi of x prime times phi of x equals to phi of x times phi of x prime. So this implies y prime y is equals to y prime. So our element y commutes with an arbitrary element of g prime. So it definitely belongs to the center. Hence, y belongs to z of g prime. So phi of zg subset of zg prime. Okay, I hope it is clear. So let's try to prove the other inclusion. Now let z belongs to z of g prime. So this is subset of g prime. So there exists an element, let's say z naught belongs to g, such that phi of z naught is equals to z. So what we need to prove? We need to prove z belongs to phi of z of g. So if we can prove that z belongs to uh, z of g, then we are done. So let's try to prove this. So let x belongs to g be arbitrary. Then phi of x belongs to g prime. So this implies phi of x times z is equals to z times phi of x, because z is in the center of g prime. Now this implies phi of x times phi of z naught equals to phi of z naught times phi of x. So this implies phi of x z naught is equals to phi of z naught x. Now uh, the map phi is bijective, so it is injective, right? So that means these two elements must be same because the images are same. So z naught commutes with x. So this implies z naught is in the center of G. So we have proved the both side. So phi of so this implies phi of z naught, which is equals to z, belongs to phi of z of G. Hence z of G prime subset of phi of z of G. So we have proved the both side inclusion. So we can conclude that phi of zg equals to zg prime. So we have proved the sixth one. Let's try to prove the seventh one. And these properties will be used when we will check two groups are isomorphic or not. So let A belongs to G, and we need to prove order of A is same as order of phi of A. Now order of A can be finite and it can be infinite also. So we need to break it into two cases. So case 1, when order of A is infinite. So we need to prove order of phi A is also infinite. So if it is finite, then what happens? Let's check. If order of phi of A, let's say it is n, which is finite, then phi of A power n should be identity of G prime. Now this is equals to phi of A power n by using the group homomorphism. Now phi is also injective. So A prime n belongs to kernel of phi, and that is the identity of G because phi is injective. So that means A power n is identity. But this is a contradiction because order of A is infinite. So order of A, phi of A, it cannot be finite. I hope it is okay. Now case 2, in which order of A, let's say it is finite and which is n. So this implies A power n is equals to identity of G. Now let's apply phi both sides. So phi of A power n is equals to phi of identity, and this is same as phi of A power n, and this is identity of G prime. So that means uh, order of phi A is finite and n divides order of phi A. So this is by the properties of order of an element, which I have done in the second season. You can go back and check. Now we need to prove it is exactly equals to n. So it cannot be less than n, right? So if order of phi of A so okay, let me write down that. Now order of phi of A is less than m. So if order of phi of A, let's say m, and it is strictly less than n, then what happens? Then phi of A power m is same as identity of G prime, and that implies phi of A power m is identity of G prime, and that will imply A power m is identity of G. And this is a contradiction, right? Because order of A is n, which is bigger than n. So hence order of phi of A is n, which is order of A. So I hope you got the proof. So if you have doubt in this, you can unmute yourself and speak. So we can move on to next problem then. Let's see some concrete problems. So suppose phi from C star dot, I hope you are well aware about this group, to C star dot be a group isomorphism. Okay. So then the problem is you need to determine the image of the element -1. So can you do this using the previous properties? Just think for a few seconds. Yeah, anyone? Can you guess what is image of -1 under phi? Okay, so let me go back to the properties. So let's look at this last property. Order of A is same as order of image of A. So uh, so what are the elements in C star which has order 2? Okay, let me write on this. So in C star dot, the element -1 has order 2. So phi of -1 has also order 2. So you need to determine which elements in C star has order 2. Can you answer now? Yes, exactly. So in C star, there exists only one element of order 2, because if you if Z belongs to C star has order 2. Okay, let me write down here. Now if Z belongs to C star has order 2, then Z square should be the identity element, right? And which is 1. So what are the solutions of this equation? So then Z has to be minus 1, right? Because the solutions are 1 and minus 1. But 1 is the identity element, so it has order 1. So Z has to be minus 1. So minus 1 is the only element in C star which has order 2. Hence, phi of minus 1 has to be minus 1. Okay, I hope you have understood this. So let me change this problem a little bit. So in this problem, what are the possibilities of phi of I? Just try it on your own. Yeah, anyone? So what are the possibilities of the image of I? Can you use the same method and guess the answer? Okay. So the element I, uh, given is phi is a group homomorphism from sister dot to sister dot. So you need to find what are the possible images of I under phi. So the element I in C star has order 4, right? So it image has also order 4 because it is an isomorphism. So you need to find which elements in C star has order 4. That means, yes, both are the possibilities of I of I. So since I and minus I are the only elements in C star which has order 4, so phi of I can be I or it can be minus I. So I hope everyone has understood this. Okay, let me move on to a next problem. So the problem is, are the groups are under addition and r star dot under r star under multiplication are isomorphic. The groups isomorphic. Yeah, can you do this? So can you guess any answer, yes or no? So if there exists an isomorphism, then what happens? So let suppose phi from r star dot to r comma plus is an isomorphism. Now minus 1 belongs to r star has order 2, right? But in this group r comma plus, the only element which has finite order is the zero element, means the identity element. So this means then phi of minus 1 has also order 2. But this is not possible, right? Because in r comma plus we have only one element of finite order, which is the 0, and whose order is 1. So which is not possible. So these two groups cannot be isomorphic. So r comma plus is not isomorphic to r star dot. Okay, I hope this is okay. So what happens if we take q comma plus and q star comma dot? Are they isomorphic? Can you use the same logic here? So we can use the same logic, right, to prove that they are not isomorphic. So by the same argument, we can say q under addition and q star dot are not isomorphic. Okay, let's move on to your next problem. So this next problem is very interesting. So that the group q plus comma dot means the positive rational numbers under multiplication is isomorphic to a proper subgroup of itself. Yeah, anyone? Can you guess what will be the subgroup? Or can you exhibit an isomorphism? So to prove two groups are isomorphic, we need to give an isomorphism between them, right? So we need to give a function between them. So uh, let me define a function. Let phi from q plus comma dot to itself be defined by phi of x equals to x square. So is this a group homomorphism? So then phi of x times y is same as xy whole square, which is same as x square times y square. So this is phi of x times phi of y. So clearly phi is a group homomorphism. Now observe that phi is in fact a injective group homomorphism. So uh, if so to prove a group homomorphism injective, what we need to prove? So we need to prove if phi is injective, if and only if its kernel is the identity, right? So we'll use this fact here. Now if x belongs to kernel of phi, so that will imply phi of x equals to identity, which is 1. So that means x square equals to 1. And the solutions of these equations are plus minus 1, right? But minus 1 is not in our domain. So the only solution is 1. So this implies kernel is equals to the identity. So phi is injective. So we can say phi from q plus comma dot to its image is a group isomorphism. Now we know that image is a subgroup of the codomain, right? which is q plus comma dot. But is it equals to q plus comma dot? Means phi is surjective or not? So the fact is phi is not surjective. Since phi is not surjective, image phi is a proper subgroup of q plus comma dot. So q plus comma dot is isomorphic to a proper subgroup of itself. But can you prove that phi is not surjective? Anyone? So you need to prove this map is not surjective. So there should exist some element in this codomain which has no pre-image, right? So can you give one element at least which has no pre-image? Yeah, can you prove this map is not surjective? If you want, you can write it in the chat box also. Non-square numbers. So let's put it simple way. Let's look at. Okay, let me write it here. Now phi is not surjective because there exists no rational number, positive rational number, such that its image is equals to 2. That means 2 has no pre-image. Because if 2 has pre-image, so what is phi of p by q? It is equals to p square by q square, right? So that means p square by q square is equals to 2. Okay, let me write it clearly. If phi of p by q is equals to 2, that will imply p square by q square is equals to 2, and that will imply p square equals to 2q square. So you just take the square root, because p and q both are positive, so that will imply p equals to root 2 times q. So this means p by q equals to root 2. But root 2 is a irrational number, right? So it cannot be written as p by q. So this is a contradiction, since root 2 is irrational. So phi is not surjective. So image phi is a proper subgroup of the codomain, which is q plus itself. So that will completes our proof. So I hope it is okay. Okay, let's do one more problem about group isomorphisms. Then I will move on to another topic. So check whether the group Q under addition and positive reals under multiplication are isomorphic or not. Just think for a few seconds. Yeah, do you have any guesses? Uh, can you say why? Okay. No, no, no. We are taking positive reals. Okay. Let me do this. So let us check what happens if there is an isomorphism. So suppose phi from q comma plus to r plus dot be a group isomorphism. Okay. Now the element 1 here should have a non-zero image because it is an isomorphism. So the image of identity should be identity, which is identity in the left hand side is 0 and identity here is 1. So phi of 0 is equals to 1. So let phi of 1 uh, equals to, let's say, x belongs to r plus. Okay. Now using this, can you find the image of all other element of q comma plus? So first let's see. Now if we add 1, let's say n times. So this is same as adding phi of 1 n times because it's a group homomorphism. Sorry, in right hand side we cannot add, we will multiply. So phi of 1 so that is same as phi of 1 power n, that means x power n, right? So phi of n is equals to x power n for all natural numbers. Okay. Now what about negative of natural numbers? So phi of minus n means the inverse of n. So this should be phi of n and its inverse. So that means x power n power minus 1. So this is x power minus n. And this is also hold for every natural number. So let's combine these two. Thus, phi of n is equals to x power n, and this is true for all integers. Okay, so we have able to find images of all integers. Now let's check for we need to check for all rational numbers, right? So let's try to check for reciprocal of integers. Now phi of, let's add 1 by n times. So this is same as phi of 1 by n product with phi of 1 by n times. So this is same as phi of 1 by n power n. But what is this one? This one is 1, right? So this implies phi of 1 is equals to phi of 1 by n power n. So that means phi of 1 by n power n is equals to x. So phi of 1 by n is equals to x power 1 by n. And this is true for all natural numbers. I hope this is clear. So what about now any rational number? Let's say phi of m by n. So this is same as phi of 1 by n and adding it m times. So this is equals to phi of 1 by n power m. So this is same as x power 1 by n whole power m. So this is x power m by n. Okay, I hope this is clear. So we have found image of every rational number, and this is exactly of this form. So phi of m by n is equals to x power m by n for all m by n belongs to q. But our codomain is R plus, right? So it contains irrational numbers too. So what will be the image of pi? Inverse image of pi. But there exists no m by n belongs to q such that pi of m by n is equals to x power pi. Yeah, can you see why? Because pi of m by n, because if pi of m by n equals to x power pi, that will imply x power m by n is equals to x power pi. But this cannot be possible, right? Because pi is irrational and m by n is rational. So this is a contradiction. So let's not write contradiction. So that means we have element in the codomain which has no pre-image. So this cannot be a bijective map. So this cannot be an isomorphism. So hence phi cannot be an isomorphism. So these two groups cannot be isomorphic. So I hope it is clear. Do you have any doubt in this? Okay. So we have done problems related to group isomorphisms. Now let's move on to normal subgroups. So this is problem number 6. Yes. Actually, that depends on the groups. You cannot say it for all groups actually. No, actually for few groups only we can say, but not for all groups. Okay, let's so this is a true false type question. So let G be a group. So I hope all of you can recall the definition of normal subgroup. So let G be a group and H comma K are two subgroups of G. Okay. Now define the set HK by take all the product small h times small k, where small h belongs to h and small k belongs to k. Okay. So the statement is this set HK is a subgroup of G. So is it true or false? Can anyone answer this? Why? So do you have any example? Is it so? No, no, you are saying this may not be a subgroup. So you need to give some example for that. Okay, so let me do this. So the fact is this may not be a subgroup always, but in some special cases it will be a subgroup. So we will come back to that later. But first let's see an example. So the answer is it is false. That means HK may not be a subgroup always. May not be a subgroup of G. So let's see one example. So in the lectures you have see the group about S3, right? In the cycle notations. So in the cycle notations, the elements are the identity element, the cycle 1 2, the cycle 1 3, 2 3, 1 2 3, and finally 1 3 2. So this is the group S3, and take H as the subgroup, identity and the element 1 2, and K as the subgroup, identity and the element 1 3. Okay, so now can you find what is HK? Anyone? So you need to multiply the elements, right? So let's see the definition. It is of the form H times K, where H is in H and K is in K. So let's try to multiply one by element, one by one. So identity times identity, identity times 1 3. Now 1 2 times identity, and 1 2 times 1 3. Now you need to multiply the elements. So identity times identity is identity. Identity times 1 3 is 1 3. 1 2 times identity is again 1 2. Now what about this last one? 1 2 times 1 3. So here, yeah. So the last one is 1 3 2. Okay. So this is the set HK. So I have claimed this is not a subgroup, and that is why, because it is not even closed under the group operation. So you take these two elements, 1 3 and 1 2. Now 1 3 times 1 2 is equals to 1 2 3. You can check this, and this does not belongs to the set HK. So this is even not closed. So HK is not closed. It cannot be a group. Hence HK is not a subgroup of S3. I hope the example is clear. So the calculations you can do it on your own. Now let's see what are the cases in which it will be a subgroup. So the fact is, if one of H or K is a normal subgroup, then this product will be a subgroup. So okay, let me write down it. So let G be a group H be a normal subgroup and K be a subgroup of G. Then HK is a subgroup of G. Okay. So I hope this statement is clear. Okay, so let's try to prove this. So to prove it's a subgroup, we need to prove three properties. Let me list down that. First one is closure. Second one is existence of identity. Third one is existence of inverse elements. So let's start with the closure. Closure means if we take two elements, then their product, then their product should also be in that set. So let A and B be two arbitrary elements in HK. But we know how the elements of HK looks like. So then A equals to some H1 times K1 and B equals to some H2 times K2, right? For some H1, H2 belongs to H and K1, K2 belongs to K. So we need to prove H1, K1 times H2, K2 belongs to HK, right? So it will also of the form some H prime times K prime. So we need to prove that only. So how can you write this element as a product of element of H and as a product of element of K? So we need to use the fact that H is a normal subgroup. Okay. So observe that this element can be written as, you keep H1 K1 as it is. Now here we have H2. Now inside K1 inverse again K1, and as we have K2. Now observe that this element is identity. So we are putting this element inside. Now this element is in H because H is a normal subgroup. This element is also in H and this is in K. So it is product of elements of H and elements of K. So let me write down it. Now K1 belongs to K, which is subset of G, and H2 belongs to H. So that implies K1 H2 K1 inverse belongs to H because H is normal in G. Okay. So H1 times K1, H2 K1 inverse is in H because H is a subgroup, and K1 K2 belongs to K. So their product H1 K1, H2 K1 inverse, K1 K2 must be in HK. But what is this element? This element is exactly equals to H1 K1 times H2 K2, right? So it is in HK. So we are done with the closure property. So closure is done, and identity is very simple. Since H and K both are subgroups, so identity belongs to both H and K. So identity belongs to H times K. So identity is also there clearly. Now let's see inverses. So let A equals to H, K belongs to H times K. So we need to prove A inverse belongs to HK, which is HK inverse. And this is same as K inverse H inverse. So how can you show this is belongs to HK? So again observe that this can be written as K inverse H inverse K times K inverse, and this element is in H because H is normal circle, and this element is in K. So we are done. So let's write this just now. K inverse belongs to K, which is subset of G, and H inverse belongs to H. So this implies K inverse H inverse and inverse of K inverse. This must belongs to H. But this is same as K inverse H inverse K. So it is belongs to H. So K inverse H inverse K, K inverse. So this must belongs to HK. But this is equals to K inverse H inverse. This is A inverse. So we are done. Hence HK is a subgroup of G. Okay, I hope the proof is clear. So one remark is we have taken H as a normal subgroup. So instead of H, if we take K as a normal subgroup, then also the result is true. So I want you to do that part on your own. I will just put that as a remark. If H is a subgroup of G and K is a normal subgroup of G, then also the product HK is a subgroup of G. So you just try to prove it on your own by exactly the similar method. I hope you will be able to do it. Okay, now let's try to see some examples of normal subgroup, some concrete examples. So this is problem number 8. So the problem is you need to determine which of the following are normal subgroup. So let me write down this. So which of the following are normal subgroups of the group GL2R? Okay, so let me write down the sets. So first one is, let's say H equals to the matrices of this form where A, B, D are real numbers and A time D is not equals to 0, means it is basically the set of all invertible upper triangular matrices of order 2 over real numbers. The second one is O2 of R, means the set of all orthogonal matrices of order 2. So A belongs to GL2R such that A transpose is identity matrix of order 2. Third one is SO2R, which is A belongs to GL2R such that A is orthogonal, means A transpose is identity and determinant of A is 1. So if you have attend my first live season, I have mentioned this as group of all orthogonal matrices or orthogonal group, and this one as the special orthogonal group of order 2. So if you have not attended, you can go back and watch the video on YouTube. Fourth one is D2 of R, means the set of all invertible diagonal matrices of order 2 over R. And the last one is, let's say H equals to A0, 0D. Okay, not, let's not write in this way. A belongs to GL2R such that determinant of A is a rational number. Okay, so can you check one by one which one of these sets are normal subgroups? Just think for few moments. Yeah, anyone? Any answer? So what should be our approach? So first you try to prove the that it is normal subgroup or not. If you stuck in any step, then look for counter examples, means that it is not a normal subgroup. So let's try to recall the definition. So to be a normal subgroup, it has to be a subgroup first, right? So a subgroup H of G is normal subgroup of G if whenever G belongs to G and H belongs to H, that will imply GH, G inverse must be in H. So if this condition is satisfied for all G belongs to G and H belongs to H, then your H is a normal subgroup. So if H is not a normal subgroup, then there exists some G in G and H in H such that GH inverse is not in H. So first you try to prove this for all G in G and H in H. If it is not happening directly, then you try to look for examples, particular examples. Okay, so let's try the first one, the group of all upper triangular invertible matrices. So first of all, this is a subgroup. This is indeed a subgroup. And why? Because product of two upper triangular matrix is again upper triangular, and inverse of upper triangular matrix is also upper triangular. So that facts you can borrow from linear algebra to prove it is a subgroup. So the question is, it is normal or not? So option A. So the fact is, it will be not be a normal subgroup. So let's write H is not a so what you can do is you just take arbitrary elements. Let's say G equals to 1012. So this is indeed in GL2R because it is an invertible lower triangular matrix. And let's take H equals to 1101. Then you can check that G inverse is equals to 10 minus 1 by 2 1 by 2, and you can check GH inverse is not in H. So you just do the calculations on your own. Instead of these matrices, you can take arbitrary matrices, suitable matrices for which this will hold. So I am just taking one example. Now let's check B. So B is O2R. So is it a normal subgroup? We have already saw that these three are subgroups in our live season 1. So is O2R a normal subgroup? Anyone have any answer? So again, O2R is not a normal subgroup. So if you recall, I have told that O2R has special form. It is of the form cos theta, sin theta, minus sin theta, cos theta, where theta is in R. So every 2 by 2 real orthogonal matrix has this form. So this is one fact which you can use. So let's take G as the earlier matrix 1 0 1 2, and let's take H. So you can take theta as let's say pi by 4. So it will be cos pi by 4 means 1 by root 2. Sin pi by 4 is also 1 by root 2. So this is in O2R. And G inverse, as we have earlier seen, 1 0 minus 1 by 2 1 by 2. So you can check G inverse is not in O2R. So you can do these calculations, and also I will upload these notes in the Google Drive. You can download it. And earlier notes are also available. You can download it. So what about SO2R? This is a subset of O2R actually. So is SO2R a normal subgroup of Gl2R? Yeah, anyone? Look, if we take the same example, this H has determinant 1 and it is orthogonal matrix. So it is in SO2R. Okay, but this is not even in O2R. So it cannot be in SO2R. So the same example works. So we can directly say SO2R is not a normal subgroup of Gl2R. So you can take the same example, take the example in B. So you can do the calculations on your own. Okay, finally, option D, D2R. Anyone? In this case, the calculations are easy. So you should say your answer immediately. So D2R is the set of all 2 by 2 invertible diagonal matrices over R. So it is already subgroup we have saw. So it is not a normal subgroup. So D2R is not a normal subgroup. So again I will take the same G, and which is 1 0 1 2, and take the diagonal matrix 2 0 0 5. G inverse is 1 0 minus 1 by 2 1 by 2, and you can check G inverse is not in D2R. So in these four examples, none of them are normal subgroup, but all of them are subgroup. Now what about the last one? This one should be easier. Which one is not a subgroup? Is it so? No, I am taking all those invertible matrix whose determinant is rational number. So you can go back to the live season 2 where we have proved that this is indeed a subgroup. So the fact is it will be a normal subgroup also. So let's do that. So we have already saw it is a subgroup. So let's write H again. A belongs to GL2R such that determinant of A is in Q. Okay, so let's take G belongs to GL2R an arbitrary element and small h belongs to H an arbitrary matrix. So we need to prove G inverse is in H, right? So what does that mean? So it if and only if determinant of G inverse is in rational number. So is it true? So what is determinant of G inverse? So use the properties of matrices. It is determinant of G times determinant of H times determinant of G inverse, right? And this is equals to determinant of G times determinant of H times 1 by determinant of G. So this will be cancelled out. So this is same as determinant of H and this is a rational number. So this implies G inverse is in H. Hence H is a normal subgroup. Okay, I hope it is clear for all of you. Okay, now let me ask some more questions from this only. So we have saw SO2R is a subset of O2R. So that means SO2R is a subgroup of O2R. So is SO2R is a normal subgroup of O2R? So we know SO2R is a subset of O2R. So SO2R is a subgroup of O2R. So is SO2R is a normal subgroup? Yeah, can anyone answer this? Yeah, it will be. So let me write down quickly. If G belongs to O2R and H belongs to SO2R, so that means G and H both are orthogonal matrices. So we know product of orthogonal matrices are orthogonal. So G inverse is also orthogonal, right? Because G inverse is also orthogonal. So it is in O2R, and determinant of GH inverse is 1. You can check this. So from this you can conclude this one. So the answer is yes. So this is first one. I want to ask one more question from here. So the interesting part is the last one, the last subgroup. So here we can take Q star also, because A is in GL2R, so determinant cannot be 0. So we can take it as Q star. So it will not affect this question. So the question is, okay, let me. So if K is a subgroup of R star under multiplication, then the set H defined by A belongs to GL2R such that determinant of A is in K. Then is H a normal subgroup of GL2R? Can you check quickly? So you need to check first if it is a subgroup or not, and if it is a subgroup, it is normal or not. Yeah, okay. Yeah, you are correct. So it will be a subgroup, and indeed it is a normal subgroup. So let me prove this. So for closure, let's say AB is in H. So then determinant of AB is same as determinant of A times determinant of B, but this is also in K, this is also in K. So their product is also in K. So AB belongs to H. And definitely the identity matrix has determinant 1, which is in K, because it is a subgroup of R star. So identity is in H. Now inverses is the same. So if A belongs to H, that means determinant of A belongs to K. So let me write down it as determinant of A inverse is in K, because K is a subgroup. So this is equals to determinant of A inverse, and it is in K. So this implies A inverse is in H. Now for normality, let G belongs to GL2R and H belongs to H. Then the obvious fact is determinant of GH G inverse is same as determinant of H itself, and it is in K. So GH G inverse is in H. So it is a normal subgroup. So this is the most general case, because K can be any subgroup of R star, right? It can be the rational numbers, it can be the positive rational numbers, it can be the positive reals also, and many other subgroups. So in all cases, it will be a normal subgroup. And in fact, this thing can be deduced from one more result. Let me write down that. So this is question number 9. So I will write down it is as an exercise. So let phi from G to G prime be a surjective group homomorphism. Okay. Okay. Also assume and n prime be a normal subgroup of G prime. Then is it true that phi inverse n prime? Okay, let me write down the set precisely. This is G belongs to G such that phi of G is in n prime. So then is it true that this set phi of n prime is a normal subgroup of G? So I want you to try this exercise, and if you are not able to do, you can ask me in the next season. I will do it for you. So you just try it on your own. I hope you are able to understand this question. So spend few minutes in this later after this live session. So we have done problems on group isomorphisms, also on normal subgroups. So two are left, cosets and Lagrange's theorem. So let's try to cover as much as possible. So before that, I want to solve a small exercise on normal subgroups, which is useful. So let 10. Then I will come to some interesting problems on Lagrange's theorem. So let G be a group and H1, H2 are two normal subgroups of G. Okay, then their intersection H1 and H2 is also a normal subgroup of G. So in earlier life seasons, we have already saw that intersection of two subgroup is a subgroup. Now we are claiming something more. Intersection of two normal subgroup is a normal subgroup. So we know, okay, let's see the proof. H1 intersection H2 is a subgroup. So we need to check the normality. So now let G belongs to G and small h belongs to the intersection. Then G inverse is in H1 because H1 is a normal subgroup. Also it is in H2 because H2 is also a normal subgroup. So G inverse is in the intersection. So we are done. So H1 intersection H2 is a normal subgroup of G. And the fact is you can take any number of subgroups, not only two, any arbitrary number. So I will just put that as remark. So the above result is true for arbitrary intersections also. So the proof is exactly the same. So you can write the details on your own. Now let's move on to the problems on Lagrange's theorem. So it is problem number 11. So this one is fairly easy but interesting. Let me write down it. So let H and K be two subgroups of a group G. Also assume order of H is 24 and order of K is 30. Yes. No, first of all, their union need not be a subgroup. Okay. So in our live season 2 that I have mentioned, union of two subgroups may not be a subgroup. So in that case, normality, there is no question on normality. So in some special cases, union of two subgroup is again a subgroup. So okay, as you have asked, let me just mention this. So okay, okay, let me write down here. So union of two subgroups H1 and H2 is a subgroup if and only if either H1 is subset of H2 or H2 is subset of H1. So you can try to prove it by yourself. or you can refer to any standard book also, or you can come back to me in the next session. That is not an issue. So in these cases, if H1 and H2 are both normal subgroups, and suppose union is a subgroup, then one of these two cases must happen. So in both cases, the union is either H2 or it is H1. So union is a normal subgroup in that case. So that is very particular case. So let's come back to our problem. So H and K are two subgroups. Order of H is 24 and order of K is 30. Then the problem is prove that H intersection K, it is also a subgroup as we have seen, but prove that H intersection K is an abelian group. Yeah, can you do this? So you have to use the Lagrange's theorem. So let me recall the Lagrange's theorem for you. So if G is a finite group and H is a subgroup of G, then order of H must divides order of G. So this is the Lagrange's theorem. Order of H will always divides the order of the main group. So using this, can you solve this one? Now see, uh, H intersection K is subset of H as well as it is subset of K. So it is a subgroup of H as well as K. Okay. So by Lagrange's theorem, order of H intersection K must divide order of H and order of H intersection K must divide order of K. Okay. So this implies order of H intersection K must divide GCD of order of H and order of K. But what is GCD of order of H, order of K? So GCD of order of H, so it is GCD of 24 and 30, right? Oh, sorry, we should take uh, 20. Let's take order of K as 20. So then GCD is equals to 4. So order of H intersection K must divides 4. So from this we can say order of H intersection K must be 1 or 2 or 4. Now if you recall the lectures, uh, we have seen every group of order less equals to 5 is abelian. So whatever the order of H intersection K, it should be abelian. Okay, so I hope the proof is clear. Okay, now let's do one more problem. A similar kind of problem. So let K be a proper subgroup of H and H be a proper subgroup of G. Now, if order of K is 42 and order of J is 420, then what are the possibilities of order of H? Just try it for a few seconds. So K is proper subgroup of H and H is proper subgroup of G, and order of K is given, it is 42, and order of G is 420. So you need to find order of H. So you have to use the Lagrange's theorem. Yes, anyone? If you want, you can put it in the chat box also. If you have any answer, or you can unmute yourself. Okay, let me do this. So K is a proper subgroup of H. So by Lagrange's theorem, order of K must divides order of H and also H is proper subgroup of G. So order of H must divides order of G. So let order of H equals to n. Okay. So then from this one we can write n equals to 42 times b1, because 42 divides n, and from this one we can write 420 equals to some n times d2 for some integers d1 and d2. So now 420 is equals to n d2, right? And this is equals to 42 times d1 times d2. So this implies, so we can cancel out this 42 from both sides. So this gives 10 equals to d1 times d2. So actually these are positive integers. So from this we can say d1 divides 10. So what are the possibilities of d1? So d1 is equals to 1 or 2 or 5 or 10. Now let's put it back in here. So n equals to 42, 42 times 2, 42 times 5, or 42 times 10. So which is equals to either 42 or 84 or 210 or 420. But see, we have assumed H is a proper subgroup of G. So order of G and order of H cannot be equal. So order of H has only three possibilities, either 42 or 84, 210, since H is a proper subset of G. So we have the only three possibilities. Okay, I hope you have understood how to use the Lagrange's theorem here. So do you have any doubt in this? Okay, so we are already over time. So I think we can wrap up now. So I will upload these notes in which here is my website. You can find the contact details of me. If you have any doubt, you can mail me. So let's just wrap up this season. So you can leave now.